The date is September of 1941, and a British cargo ship called the Empire Liberty has just been delivered to the Ministry of War Transport at a yard on the Wear River in Sunderland, England. She is not beautiful. She is not fast. She displaces 14,000 tons of steel, rides low in ballast, and her triple expansion steam engine drives her at 11 knots, which is barely fast enough to outpace a surface submarine in calm water. The men who built her took 230 days to do it. The men who designed her were not trying to win a design award. They were trying to solve a calculation that was threatening to strangle the Allied war effort before it fully started. German U-boats were pulling merchant ships out of the Atlantic at a rate that the shipyards of Britain and America could not keep pace with. Every week the ledger ran the same way. Tonnage sunk against tonnage launched, and the sunk column kept winning. In the first 8 months of 1942 alone, U-boats sank more than 500 Allied merchant vessels in the Atlantic. The mathematics of that loss extended far beyond the ships themselves. Every torpedoed tanker was several months of aviation fuel that never reached an airfield. Every sunken freighter was a cargo of locomotives, or field rations, or truck tires, or medical supplies, specific and irreplaceable, items that a quartermaster somewhere was waiting for and would not receive. The war in North Africa moved at the speed of fuel delivery. The war in the air moved at the speed of spare parts. Everything that held the Allied effort together was moving across water that German submarines were methodically turning into a graveyard. If this story is pulling you in, take a second to hit the like button and subscribe, and drop a comment telling me where in the world you're watching from. It means a great deal to know who's listening. The math behind that number was not merely logistical. Every lost ship was a lost crew. Every lost hull was thousands of tons of fuel, ammunition, food, and equipment that never reached a port, never reached a depot, never reached the soldier or the aircraft or the tank that needed it. What the Allies needed was not a beautiful ship. They needed a ship that could be built faster than the enemy could sink it, in quantities that no single nation had ever produced, by workers most of whom had never set foot inside a shipyard. What they got, eventually, was the Liberty ship. What made it possible was a set of decisions made at yards in Baltimore, Richmond, Portland, and Houston. Decisions about steel, about fire, about how a whole comes together, that changed the arithmetic of industrial war. And at the center of those decisions, working in the noise and smoke of a California shipyard on the Richmond waterfront, was a man named Henry Kaiser, a contractor who had never built a ship before in his life, and around him a workforce of welders, many of them women, many of them black Americans given their first industrial jobs by the sheer pressure of wartime necessity, who between them turned 230 days into 4.5. The Liberty ship program began with a British order. In September of 1940, Britain placed a contract with an American consortium for 60 cargo vessels, each built to a simplified version of the Ocean-class design that Sunderland yards were already producing. The specification was deliberately conservative. Triple expansion reciprocating steam engines rather than turbines, because turbines required precision manufacture and months of lead time. A 5-hole layout. Riveted hull construction, at least initially, because riveting was understood and American yards were full of riveters. The ships were ugly by the standards of naval architecture, and their designers knew it. Admiral Emory Land, chairman of the United States Maritime Commission, called them a necessary, ugly duckling. What they were, more precisely, was a minimum viable hull, the least ship you could build and still move cargo across an ocean. President Roosevelt announced the emergency program in January of 1941. The Maritime Commission set a target of 200 ships in the first year. Within months, that target would be revised upward, then revised again. The question hanging over every shipyard superintendent in the country was the same one that had defined every major production problem of the war. Could you build the thing faster without making it fall apart? Riveting was slow. A riveting gang, one heater, one catcher, one bucker, one riveter, could drive somewhere between 300 to 500 rivets per 8-hour shift. A Liberty ship required roughly 250,000 rivets in its hull. The arithmetic worked out to months. Welding was faster. An arc welder could fuse a seam in a fraction of the time it took a riveting gang to close the same joint, and a welded seam, done correctly, was stronger than a riveted one because the join was continuous rather than a series of discrete points. The problem was that done incorrectly, a welded seam was not stronger. It was a crack waiting to open. The shift from riveting to welding in American shipyards between 1941 and 1943 is not a single decision. It is 1,000 decisions made at different yards by different foremen and engineers, each one a bet on how far you could push the speed of fabrication before the quality of the hull started to degrade. At Kaiser's Richmond yards, those bets were placed faster and harder than anywhere else on the American coast. Henry Kaiser had built Hoover Dam and the San Francisco-Oakland Bay Bridge. He understood large-scale logistics, subcontractor coordination, and the kind of organizational pressure that gets men to work faster without working them to death. What he did not understand at the start was ships. His chief naval architect, a man named George Sharp, had to explain to him the basic vocabulary of shipbuilding in their first meetings. Kaiser absorbed it, then immediately began looking for the parts of the process that could be rearranged. The standard method was linear. You laid the keel, added frames, built up the hull plate by plate, added the superstructure, fitted the machinery, floated the hull, completed outfitting at a dock. Each stage waited for the previous one to finish. Kaiser looked at that sequence and saw dead time. Workers waiting for a section to be positioned before they could start, cranes idle while men finished a weld, machinery sitting on the dock waiting for a hull to arrive. What he proposed instead was prefabrication. The hull would not be assembled in place, piece by piece. It would be assembled in sections. Large prefabricated units, built flat on the ground in the fabrication shops, fitted with their internal components while horizontal, then lifted by crane and welded to the growing hull in a matter of hours rather than days. The logic was similar to what a factory floor manager would recognize immediately. You parallelized the work. While the hull was being framed, the sections that would attach to it were already being completed in another part of the yard. The fabrication shops ran independently of the ways. A section being built on the flat could be fitted with pipe runs, valves, electrical conduit, ladder brackets. Everything that would have taken workers hours to install in the cramped interior of a half-assembled hull could be done while it was still horizontal and accessible. When the hull was ready, the sections came off the fabrication floor substantially finished and dropped into place. A Liberty ship is a large steel box divided into 5 holds. The bow section, the stern section, the engine room amidships, the deck house, the holds themselves. Each one could be built as a discrete unit and then assembled. At Richmond, Kaiser pushed the size of those prefabricated units as far as the yard's cranes could lift. Then he bought bigger cranes. The prefabricated units grew from units weighing a few tons to units weighing 60, 70, 80 tons, pre-plumbed and pre-wired and pre-fitted with pipe runs and cableways and insulation before a crane ever picked them up. When the unit arrived at the hull, the work of fitting out that section was already done. The cranes set it into place, the welders closed the seam, and the next unit was already on its way from the fabrication shop. The first ship Kaiser's Richmond No. 1 yard completed was the Ocean Vanguard, delivered in October of 1941. Build time, 150 days. That was already faster than the Sunderland average. But the Maritime Commission's contracts were about to force the pace much harder, and the yards were about to discover something that Kaiser's optimism had not fully accounted for. Welded steel under stress cracks differently than riveted steel. In a riveted hull, when a crack propagates through one plate, it stops at the rivet holes in the boundary of that plate. The hull can fail locally without failing catastrophically. In a welded hull, the entire structure is continuous. A crack that starts in one weld does not stop at a boundary. It travels. In the winter of 1942 and 1943, Liberty ships began breaking apart. Not slowly. Suddenly. The John P. Gaines cracked amidships in the Bering Sea on November 10, 1943. The Schenectady split in two while tied up at a fitting-out dock in Portland, Oregon, on January 16, 1943, in weather that was calm and mild, the temperature 33 degrees Fahrenheit, and the hull simply opened along a transverse fracture that ran from the deck down through the keel. The failure happened in the dark and took less than a minute. The bow section swung 90 degrees into the dock and grounded. The stern settled. The noise, witnesses said, was like a rifle shot that kept going. The ship had been in service for less than a year. She had not been at sea. She had not been under stress from wave loading or torsion or any of the forces that a hull is built to resist. She had been sitting in calm water, and the thermal contraction of the steel in near-freezing temperatures had been enough to run a fracture along a line of continuous weld that connected one stress concentration to another across the full width of the hull. The Misso cracked. The SO Manhattan cracked. The service records of the first 1,000 Liberty ships show nearly 700 stress fractures of varying severity. 146 ships suffered fractures bad enough to threaten structural integrity. 19 broke completely in two. The problem was not, as the Bureau of Ships initially suspected, that the welders were incompetent. Many of them were newly trained. Yes. Kaiser had put 400,000 people through welding courses in California alone, many of them women recruited directly from domestic work and farm labor and retail, many of them black workers hired despite the explicit resistance of the Boilermakers Union, which maintained segregated Local A and Local B structures throughout the war. Black workers at the Richmond yards were assigned to auxiliary locals with limited seniority rights and were formally barred from certain job classifications regardless of demonstrated skill. The Congress of Racial Equality organized protests at the yards in 1943, and the Fair Employment Practices Committee investigated the Boilermakers' practices and found them in violation of the executive order banning discrimination in war industries. The program hired anyway, and the black workforce at Kaiser's Richmond yards reached into the thousands despite the union's obstruction, because the yards needed welders and the welders were there. The welding schools ran for 6 weeks. An experienced shipyard welder of the pre-war years had typically served 3 to 5 years as an apprentice before being certified for structural work on a hull. Kaiser's program compressed that into 42 days of intensive instruction, and the workers who came out of it were not master welders by any peacetime standard. They were production welders, trained to run a specific set of joints at a specific quality level on a specific hull design. The Liberty ship hull was broken down into a catalog of weld types, each one classified by position, joint configuration, and accessibility, and a production welder was trained to do the welds in that catalog and no others. The redundancy built into the system, inspection, radiographic testing of sample plates, pull testing of test coupons welded by each certified operator, was partly a concession to the reality of the workforce's experience level. But the fractures were not primarily human error. They were material science. The steel used in Liberty ship hulls had a higher sulfur content than was ideal for welded construction. In cold water, and the North Atlantic and the Bering Sea are cold, the steel underwent a transition from ductile to brittle behavior at temperatures that the ships regularly encountered. A welded hull in cold, rough water was accumulating stress at notch points, corners, hatch openings, the transitions between the deck plate and the side plate. At those points, the continuous weld that made the hull strong in normal conditions became the path along which a brittle fracture could run at the speed of sound. The geometry of the hull's own strength became its greatest liability. The investigating team assembled after the Schenectady failure included metallurgists from the California Institute of Technology, naval architects from MIT and the Webb Institute, and steel manufacturers who had to be told, in some cases, that specifications they had been meeting for 30 years were inadequate for this specific application. What they found over 18 months of analysis, pulling records from fractured ships, examining fracture surfaces under laboratory conditions, running load tests on sample plates at reduced temperatures, was a set of findings that reshaped how every remaining Liberty ship was built for the duration of the war. The changes were not glamorous. They were the kind of engineering corrections that do not appear in newsreels and are not painted on recruitment posters, but they are the reason the program did not collapse under its own fracture statistics. If this is the kind of history you want more of, subscribe and turn on notifications. There's far more in the record still to cover. Your support is what keeps these stories coming. Crack arrestors were sewn into the hull structure at regular intervals. Short sections of riveted construction inserted deliberately into the otherwise all-welded frame, specifically at the locations where transverse fractures were most likely to propagate. If a weld cracked, it would run until it hit one of these riveted interruptions, and there it would stop. The principle was borrowed directly from the behavior of the old riveted hull, grafted onto the new welded one as a controlled disruption of the continuous structure. Installing them required yards to train a subset of their workforce in riveting, a skill the program had been trying to eliminate, and to maintain riveting gangs alongside their welding crews for the specific purpose of placing these interruptions. It was an engineering admission that the fully welded hull was not yet fully understood. That admission, running against everything the program was trying to achieve in terms of speed and simplicity, saved ships and the men who sailed them. Weld wire chemistry was tightened. The composition of the welding electrodes was revised to reduce hydrogen introduction into the weld pool, one of the identified drivers of the brittle fracture mechanism. Preheat requirements were introduced. Welders working on high-stress joints were required to bring the base metal to a minimum temperature before striking the arc, which reduced the thermal gradient in the heat-affected zone and decreased the residual stress that had been propagating the fractures. The square corners of hatch openings, where stress concentrated in predictable patterns, were redesigned with radius corners that distributed load over a wider area. These were not innovations in the sense of new ideas. They were corrections derived from failure analysis, applied systematically to a production program that had been moving too fast to catch the problem before the problem caught up with it. These changes did not make the cracking problem vanish immediately. Ships continued to fracture into 1944, but the rate dropped, and the severity dropped, and the hulls that broke continued to be replaced by new ones faster than they were lost. None of this, however, accounts for the most cited single event in the Liberty ship program's production history. In November of 1942, Kaiser's Richmond No. 2 yard laid the keel of hull No. 440. The ship was named the Robert E. Peary, after the Arctic explorer. The Maritime Commission had proposed a demonstration, a record build, documented from keel laying to launch, to show Congress and the press what American industrial capacity could achieve. Kaiser accepted. The Robert E. Peary went from keel to launch in 4 days, 15 hours, and 26 minutes. She was delivered, fitted out, and ready for sea 7 days later. The record was real. It was also, in important ways, a controlled demonstration rather than a standard production run. Sections that would normally be fabricated during the build cycle had been pre-staged before the keel was formally laid. The yard shifted workers from other projects to concentrate on hull 440. The cranes ran 24 hours on rotating crews. The record stood and stands, but the 4-day ship was not the average Liberty ship build time, even at Richmond's peak efficiency. The average, at Kaiser's best yards in 1943, was around 42 days from keel to delivery. That was still a transformation from the 230 days of the first ocean-class deliveries in Britain. What had compressed 230 days into 42 was not a single genius move or a single genius welder. It was a systematic reimagining of how a whole comes together, applied by hundreds of thousands of workers who had been handed a torch and told that the course of a war depended on the quality of their seams. The rhythm of a Kaiser yard at full production was precise and fragile. Sections were numbered and tracked on boards that showed the position of every major unit in the fabrication sequence. A section that fell behind pulled everything behind it, because the assembly was not a line in the factory sense. It was a set of interdependent sequences, and the hull on the ways was the convergence point for all of them. Every yard ran 3 shifts. Workers who had been riveting iron on a San Francisco streetcar line 6 months earlier were now running a continuous bead on a prefabricated stern section at 2 in the morning, working in the noise of a dozen other welders on either side, with an inspector who would pull the section for radiographic testing if the bead showed discontinuities. The inspector was not there to punish anyone. A failed weld that left the yard was a sailor's life. By 1943, Richmond was producing a Liberty ship every 10 days per way, across 4 active shipways per yard. Across all Kaiser yards on the Pacific coast, the output was measured in dozens per month. Across all American yards combined, the Maritime Commission was delivering a completed Liberty ship every day. Then, from mid-1943, faster than a day. By the end of the war, American yards had delivered 2,710 Liberty ships. Another 531 of the slightly improved Victory ship design followed the same basic production model. The U-boats had sunk hundreds of merchant vessels in the first 3 years of the war. American yards replaced them faster than the submarines could find them, and then kept building past any conceivable replacement rate until the Atlantic was no longer a contested supply line, but a sustained ferry service moving material from North American ports to every theater where the Allies were fighting. A Liberty ship carried 10,000 tons of cargo. One ship could carry enough artillery shells to supply a division in combat for several weeks. Enough food to feed an army for months. Enough aviation fuel to run a bomber group through a sustained campaign. The ships that sailed from Richmond and Baltimore and Houston in 1943 and 44 were not individual vessels. They were the logistical lifeblood of an expeditionary war being fought on 4 continents. And the fact that they were arriving faster than they could be sunk meant that the flow of material to every theater, North Africa, Italy, Britain before Normandy, the Pacific, could be sustained and then accelerated past the point where any enemy interdiction strategy could reverse it. Admiral Karl Donitz, commander of the German submarine arm, understood the arithmetic before the war's midpoint. He wrote in his war diary in the summer of 1943 that the tonnage being launched by American yards had made the campaign against Allied shipping operationally unwinnable. The U-boats could sink individual ships. They could no longer affect the aggregate supply rate. The calculation that had nearly strangled Britain in 1941 had been inverted, and the inversion was complete. The decision to shift from riveting to welding, the decision to prefabricate in large sections, the decision to hire anyone who could be trained regardless of race or sex, the decision to design for production simplicity rather than engineering elegance. These were not a sequence of inspired breakthroughs. They were a series of industrial and organizational bets placed under pressure, refined by failure, corrected by metallurgists and engineers who had to solve problems the program, created by its own speed, and ultimately vindicated by a production record that no nation has matched before or since. The Robert E. Peary is frequently cited as the culmination of this story, and the 4-day build is the number that survives in popular history. The number is real. The ship was real. She served until 1963, when she was scrapped in Baltimore. But she was a record set under controlled conditions, not the daily reality of the program. The daily reality was a 42-day hull produced by a workforce of largely untrained civilians who had been handed welding torches and told that the course of a war depended on the quality of their seams. The reality was the women of Richmond working night shifts in the cold-off San Francisco Bay, running beads on prefabricated sections that would become the bottom of someone's cargo hold in a convoy crossing the North Atlantic. The reality was the black workers who found their first industrial employment at Kaiser's yards because the labor shortage had made discrimination an operational liability the program could not afford, even as the union structures that surrounded them continued to resist their advancement at every level above the production floor. The reality was the metallurgists who spent 18 months tracking fracture patterns through cold water wrecks and eventually told the yards, precisely and specifically, where the welds were failing and what to change. The reality was the crack arrestors, ugly and unglamorous, sewn into hulls that would otherwise have split open in the North Atlantic winter. Those ships, not the Robert E. Peary alone, are the reason the ledger turned. The record that matters is not 4 days, 15 hours, and 26 minutes. It is 2,710 ships in 4 years, built by people who had never built a ship, out of steel that cracked, and had to be redesigned in the middle of production, using a welding technique that the industry had never applied at scale, managed by a man who had learned what a keel was the year before he started laying them. The German naval staff looked at that number, ran their own projections on the rate at which Allied tonnage was accumulating, and concluded in writing that there was no longer any mathematical path to victory through submarine warfare. Every ship they sank was replaced. Every ship that replaced it carried cargo. The cargo fed, fueled, and armed armies that were closing on Germany from 3 directions at once. Most of the workers who built them are gone. The yards at Richmond were demolished after the war, and the site is now a park on the bay waterfront, with a small museum that holds photographs of the women and men who worked the night shifts in the fog. A few Liberty ships survive in preservation. The SS Jeremiah O'Brien, based in San Francisco, is one of 2 still in operating condition. She was built at the New England Shipbuilding Corporation yard in South Portland, Maine, in 1943, in 56 days. She sailed as part of the Normandy invasion fleet on June 6, 1944, carrying cargo to the beaches while naval gunfire and aircraft made the sky overhead something other than sky. She returned to Normandy 11 times that summer, running back and forth between England and the French coast, before being laid up in San Francisco in the post-war years. She was preserved in 1979, restored to operating condition by volunteers, and is still capable of getting underway today. When she does, her triple expansion steam engine turns at a pace that sounds like a very large heart, and her hull moves through the water at the same 11 knots that her designer specified in a meeting in 1940. She is not beautiful by the standards of naval architecture. She was never meant to be. She was meant to get to the other side. Thank you for staying with us until the end. If what you heard here stayed with you, the other films on your screen carry the story forward. Subscribe if you haven't, and I'll see you in the next one.